Section 8 of the Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 2. Edited by Francis Rolt Wheeler. Geology. Chapter 4, Part 2. Leopold von Buch, 1774 to 1852, was the most illustrious of the geologists taught by Werner. He was born in the castle of Stolp in Pomerania, the son of a nobleman with considerable property. While still a boy, he displayed a passionate love of scientific inquiry, and his fondness for chemical and physical mineralogical studies led him to select the Mining Academy of Freiburg for his collegiate course. While there, Alexander von Humboldt and Freiesleben were among his fellow students, and with them he formed close ties of friendship. He made his home for nearly 3 years, 1790 to 1793, with Professor Werner, for whom he entertained the deepest sentiments of reverence and friendship, and these were in no way altered when, in after years, some of his opinions began to diverge from the teaching of Werner. Von Buch examined the raised beaches and terraces of Scandinavia and came to the conclusion that the Swedish coast was slowly rising above the level of the sea. In this he agreed with the opinion that had been formed by Playfair with regard to the raised beaches of Scotland. In 1809 von Buch was chiefly engaged in the mineralogical and geological researches in the Alps. Meanwhile, great interest had been roused throughout Europe by the results of von Humboldt's brilliant volcanic studies in Central and South America, and von Buch determined to make a special study of some volcanic district. Accompanied by the English botanist Charles Smith, he visited the Canary Isles and in 1815 convinced himself that they had been the center of intense volcanic activity. In his famous monograph, A Physical Description of the Canary Islands, published in 1825, he enunciated his hypothesis of upheaval craters and distinguished between centers and bands of volcanic action. In 1817 he traveled to Scotland and visited Staffa and the Giant's Causeway. When he again returned to the Alps, he renounced the Wernerian doctrines of the origin of basalt and other volcanic rocks, and ascribed the upheaval of the Alps to the intrusion of igneous rocks. At the time when Werner was in the zenith of his fame, during those 70s and 80s of the 18th century when young geologists were flocking to hear the wisdom from the lips of the prophet of geognosy in Freiburg, a private gentleman, living quietly in Edinburgh, was deliberating and writing a work on the earth's surface that will live forever in the annals of geology as one of its noblest classics. His work and that of his contemporaries is ably reviewed by Carl von Zittel. James Hutton, 1726 to 1797, the author of the famous Theory of the Earth, was the son of a merchant and received an excellent education at the high school and university of his native city. His strong bent for chemical science induced him to select medicine as a profession. He studied at Edinburgh, Paris, and Leyden, and took his degree at Leyden in 1749, but on his return to Scotland he did not follow out his profession. Having inherited an estate in Berwickshire from his father, he went to reside there and interested himself in agriculture and in chemical and geological pursuits. From his early days he had always taken a delight in studying the surface forms and rocks of the earth's crust, and had lost no opportunity of extending his geological knowledge during frequent journeys in Scotland, England, in northern France, and the Netherlands. At last Hutton set himself to the work of shaping his ideas into a coherent, comprehensive form, and in 1785 read his paper on The Theory of the Earth before the Royal Society of Edinburgh. The publication of the work attracted little favorable notice, partly due to the involved, unattractive style of writing. In larger measure, however, it was due to the fact that the learning of the schools had no part in Hutton's work. For the best part of his life he had conned them, tossed them in his mind, tested them, and sought repeated confirmation in nature before he had even begun to fix them in written words or cared to think of anything but his own enjoyment of them. Hutton's work was projected upon a plane half a century beyond the recognized geology of his own time. Hutton's audience of geologists had to grow up under other influences than polemical discussions between Neptunists and Plutonists, and had to learn from Hutton himself how to tap the fountain of science at its living source. In 1793, a Dublin mineralogist, Kirwan, attacked Hutton's work, and the great Scotsman, now advanced in years, resolutely determined to revise his work and do his best by it. Valuable additions were made and the subject matter brought under more skilful treatment. In 1795 the revised work appeared at Edinburgh in independent form and in 2 volumes. It was his last effort. He died 2 years later from an internal disease which had overshadowed the closing years of his life. The original treatise of Hutton is divided into 4 parts. The first 2 parts discuss the origin of rocks. The earth is described as a firm body, enveloped in a mantle of water and atmosphere, and which has been exposed during immeasurable periods of time to constant change in its surface conformation. The events of past geologic ages can be more satisfactorily predicted from a careful examination of present conditions and processes. The earth's crust, as far as it is open to investigation, is largely composed of sandstones, clays, pebble deposits, and limestones that have accumulated on the bed of the ocean. The limestones represent the aggregated shells and remains of marine organisms, while the other deposits represent fragmental material transported from the continents. In addition to these sedimentary deposits of secondary origin, there are primary rocks, such as granite and porphyry, which, as a rule, underlie the aqueous deposits. In earlier periods, the earth presented the aspect of an immense ocean, surmounted here and there by islands and continents of primary rock. There must have been some powerful agency that converted the loose deposits into solid rock and elevated the consolidated sediments above the level of the sea to form new islands and continents. According to Hutton, this agency could only have been heat. It could not have been water, since the cement material, quartz, felspar, fluorine, etc., of many sedimentary rocks is not readily soluble in water and could scarcely have been provided by water. On the other hand, most solid rocks are intermingled with silicious, bituminous, or other material which may be melted under the influence of heat. This suggested to Hutton his theory that at a certain depth, the sedimentary deposits are melted by the heat to which they are subjected, but that the tremendous weight of the superincumbent water causes the mineral elements to consolidate once more into coherent rock masses. He applied this theory of the melting and subsequent consolidation of rock material universally to all pelagic and terrestrial sediments. In the third part, it is shown that the present land areas of the globe are composed of rock strata which have consolidated during past ages in the bed of the ocean. These are said to have been pushed upward by the expansive force of heat, while the strata have been bent and tilted during the upheaval. Hutton next describes the occurrence of crust fissures both during the consolidation of the rock and during the elevation of large areas and the subsequent inrush of molten rock or mineral ores into the fissures. He regards volcanoes as safety valves during upheaval, which by affording exit at the surface for the molten rock magma and superheated vapors prevent the expansive forces from raising the continents too far. The evidences of volcanic eruption in the older geological epochs are next discussed. Hutton expresses the opinion that during the earlier eruptions the molten rock material spread out between the accumulated sediments or filled crust fissures, but did not actually escape at the surface. Consequently, that the older rock magmas had solidified at great depths in the crust and under enormous pressure of superincumbent rocks. He calls the older eruptive rocks subterraneous lavas, and includes among them porphyry and the whinstones, EQ trap rock, greenstone, basalt, whack, amygdaloidal rocks. Granite was also added in a later treatise. Hutton points out that the subterraneous lavas have a crystalline structure, whereas those that solidify at the surface have a slaggy or vesicular structure. In the fourth part, Hutton concentrates attention on the pre-existence of older continents and islands from which the materials composing more recent land areas must have been derived. He likewise discusses the evidence of pre-existing pelagic, littoral, and terrestrial faunas from which existing faunas must have sprung. But, he continues, the existence of ancient faunas assumes an abundant vegetation, and direct evidence of extinct floras is presented in the coal and bituminous deposits of the Carboniferous and other epochs. Other evidence is afforded in the silicified trunks of trees that occasionally are found in marine deposits and have clearly been swept into the sea from adjacent lands. Hutton then sets forth, in passages that have become classic in geological science, the slow process of the subaerial denudation of land surfaces. He describes the effects of atmospheric weathering, of chemical decomposition of the rocks, of their demolition by various causes, and the constant attrition of the soil by the chemical and mechanical action of water. He elucidates with convincing clearness the destructive physical, chemical, and mechanical agencies that affect the dissolution of rocks, the work of running water in transporting the worn material from the land to the ocean, the steady subsidence of coarser and finer detritus that goes on in seas and oceans, lakes and rivers, and the slow accumulation of the deposits to form rock strata. Hutton impresses upon his readers the vastness of the geological eons necessary for the completion of any such cycle of destruction and construction. In proof of this, he calls attention to the comparative insignificance of any changes that have taken place in the surface conformation of the globe within historic time. Hutton was thus the great founder of physical and dynamical geology. He for the first time established the essential correlation in the processes of denudation and deposition. He showed how, in proportion as an old continent is worn away, the materials for a new continent are being provided, how the deposits rise anew from the bed of the ocean, and another land replaces the old in the eternal economy of nature. The outcome of Hutton's argument is expressed in his words, quote, "that we find no vestige of a beginning, no prospect of an end." End quote. When Hutton's theory of the Earth's structure is compared with that of Werner and other contemporary or older writers, the great feature which distinguishes it and marks its superiority is the strict inductive method applied throughout. Every conclusion is based upon observed data that are carefully enumerated, no supernatural or unknown forces are resorted to, and the events and changes of past epochs are explained from analogy with the phenomena of the present age. Hutton's explanation of the uprising of continents, owing to the expansive force of the subterranean heat, was not altogether new, nor was it satisfactory. Neither had Hutton any clear conception of the significance of fossils as affording evidence of a gradual evolution. Yet in spite of these disadvantages, Hutton's theory of the Earth is one of the masterpieces in the history of geology. Hutton's genius first gave to geology the conception of calm, inexorable nature working little by little, by the raindrop, by the stream, by insidious decay, by slow waste, by the life and death of all organized creatures, and eventually accomplishing surface transformations on a scale more gigantic than was ever imagined in the philosophy of the ancients or the learning of the schools. Hutton's scientific spirit and genial personality won for him many friends and adherents among the members of the Edinburgh Academy. The most distinguished of these were Sir James Hall and the mathematician John Playfair. Hall, 1762 to 1831, contested the validity of the opinion held by some of Hutton's opponents, that the melting of crystalline rocks would only yield amorphous glassy masses. Hall followed experimental methods. He selected different varieties of ancient basalt and lavas from Vesuvius and Etna, reduced them to a molten state, and allowed them to cool. At first he arrived only at negative results, as vitreous masses were produced, but then he retarded the process of cooling and actually succeeded in obtaining solid, crystalline rock material. By regulating the temperature and the time allowed for the cooling and consolidation, Hall could produce rocks varying from finely to coarsely crystalline structure, and he therefore proved that under certain conditions, crystalline rock could, as Hutton had said, be produced by the cooling of molten rock magma. Hall then put to the test Hutton's further hypothesis that limestone was melted and recrystallized in nature. To this hypothesis the objection had been made that the carbonic acid gas must escape if limestone were brought to a glowing heat and the material would be converted into quicklime. This was Hall's first experience. Then he devised another experiment. He introduced chalk or powdered limestone into porcelain tubes or barrels, sealed them and brought them to a very high temperature. The carbon dioxide gas could not escape under these conditions. The calcareous material was thus subjected to the enormous pressure of the imprisoned air and converted into a granular substance resembling marble. Hall also conducted experiments on the bending and folding of rocks. He spread out alternate horizontal layers of cloth and clay, placed a weight upon them, and subjected them to strong lateral pressure. These and similar experiments have often been repeated within recent years, and it is well known that in this way phenomena of deformation can be artificially produced which bear the closest resemblance to the phenomena of rock deformation under natural conditions. In his desire to vindicate Hutton's theory, Hall became himself one of the great founders of experimental geology. At the same time, John Playfair, 1748 to 1819, whose interest in geology had been roused by Hutton's companionship, became the enthusiastic exponent of Hutton's theory. It was Playfair's literary skill that opened the eyes of scientific men to the heritage Hutton had left for them. He did for Hutton's teaching what 50 years after was done for Darwin's doctrines by the gifted Huxley. Playfair's Illustration of the Huttonian Theory is a lucid exposition of that theory in the form of 26 ample discussive notes. Playfair's work differs in no essential point from the views held by his master and friend, but many subjects which receive a subordinate treatment in the theory of the earth are brought into prominence by Playfair and placed for the first time on a firm scientific basis. His treatment of valley and lake erosion is extremely able, and Playfair was the first geologist who realized that the huge erratic blocks might have been carried to their present position by former glaciers. His insight in this respect would have alone won him for a lasting fame, for the erratics on alpine slopes and plains had long been observed by geologists, and an explanation vainly sought. End of Section 8. Recording by Grognor.